All right, well, I hope you guys all find this interesting. It's definitely not nearly as cool as Stefan's was. But, so when I joined iRobot, I got to work on a sea glider program. So it's an unmanned underwater vehicle, basically used to do a lot of monitoring of the world, used a lot of climate science, military applications, different things like that. And I just got introduced to a whole set of sensors and different technologies that get used. It was pretty impressive, actually seeing how much data is collected, and I thought I might share that. And maybe somebody's interested, you can actually get a lot of this data online. It's publicly available. So I'll go ahead and get started. So what is oceanography? There's 4 major branches: biological, chemical, physical, and geological. For the most part, we dealt more with the physical space, but these vehicles actually support all of these different things. The biggest thing I noticed was that the ocean is pretty huge. It's really, really big, and there's a lot of data to be collected. This data feeds into oil and gas collection, climate science, military applications, and for the most part, people want to collect it all the time. So how do we monitor it? There's moored sensors that get placed in the ocean. There's things like this that are on the surface. There's other types of sensors which are moored to the ocean floor that are slightly underneath the surface. All of these things are in dangerous locations. They can get hit by boats and ships. They can get dislodged. They're also very difficult to get to access, to maintain. So we have boats. Boats are expensive. They can cost in excess of $50,000 a day per ship. You're trying to cover a very large area, so there's many, many of these ships. They're not affordable for most scientists. If you can't afford a research assistant, there's a really good chance you can't afford a boat either. We had a lot of researchers who would be like hitching rides on boats that were going in the right direction so they could get their research done. They're capable of limited surface measurements. Trying to extend a cable 1,000 meters underneath the surface of the water is very difficult. You end up with some interesting hydrophone configurations like this that actually have wings, so that ships can drag them behind them and they won't just spin around in the air, or around the water, sorry. This is just a couple of pictures of several of the ships that I found online, and lots of other boats. There's many boats. This is a very, very large space. We also use things called floats. They literally do that. They just float. Some of them on the surface. Others can change their buoyancy, and they can move up and down throughout the water column. They can't actually really direct themselves. They're, for the most part, dropped into a specific location. People understand the water currents around the area, and then they go pick them up later. They have either satellite connections, or they're using some other sort of satellite technology to actually tweet their data back. Or sometimes they're just dropped and picked up later and then downloaded. They don't even have live feeds of data. There's lots of floats. This is a picture of data collection points from all over the world where floats have been placed. These things, they float, so they can't actually station keep and stay where they are. They're expensive to deploy. You have to redeploy them and redeploy them, and again, and again, and again. And there's goats. There's not actually goats, it just rhymes. Or you could use an autonomous underwater vehicle, or AUVs. These vehicles can station keep. They do have some basic flight capabilities. There's many, many different designs. This is a wave glider. You have other things like the Slocum glider here, and then the sea glider is way over there on the left. They have a lot of different capabilities. The wave glider is mainly a surface vehicle. It doesn't get very deep. Slocum glider can go down a little bit more, maybe, I don't know, 100 meters or so. And then you have vehicles like the sea glider that go down to 1,000 meters, which actually isn't still deep enough. A lot of researchers want vehicles that can go down to 5,000 meters or more. Those kind of vehicles are under development, but there's a lot of challenges from a physics perspective. When you get that deep, the body of the vehicle starts to crush, even though it's a solid block of aluminum, a solid tube of aluminum. That affects the density, and you can sink pretty easily. Many of these vehicles are capable of staying out in the ocean for many, many months. Sea glider has, I think, the longest recorded mission of, I think it's about 9 months of time spent at sea. Some of these vehicles have problems in that they have movable articulating parts, like here on the end. Those tend to get gunked up with things that are in an environment where there's plants growing, fish attaching to them, things like that. That's actually one of the biggest drawbacks to a vehicle like this or like this. You have to intermittently go out and find them and then service them. And so if it's a 2-month transit out to your vehicle, you don't want to do that very often. It's not something a lot of people want to take on. You can also reach many difficult places, places where ships can't go, under ice, near icebergs. We actually had a vehicle lost while I was trying to measure some volcanic activity. Probably wasn't a good idea. Oil leakages, when the Deepwater Horizon spill happened, we actually sent a sea glider down there. We weren't actually able to get deep enough to really get into the oil plume. We could only skim the top. We got it at about 1,000 meters, and that actually wasn't enough. We also developed radiation sensors, and we sent some of those over to Fukushima to try to measure radiation in the water column, see how it might be affecting fish life. We were working with the fisheries in Japan. They measure many different things. There's some pretty standard sensors that people put on board these things. Conductivity sensors to measure salinity, dissolved oxygen. There's so much science that comes out of some of these things. It's incredible. Sensors are used for multiple types of missions. We developed this thing here. It's a glider-mounted acoustic Doppler current profiler, which was funded in order to count shrimp in the water. But what it actually did that most people were interested in is measure the velocity of water underneath the vehicle, and from that we could calculate ground Earth reference velocity. So we could do under ice measurements without having to put out beacons or any sort of extra sensory technology like that. We worked on some cool mammal detection stuff, tracking whales and things like that. They do some long baseline interferometry. They basically go out and collect a lot of data, track the location of that data to bring it back in a lab and start to do some correlations on it. Lots and lots of different things. I have no idea what microstructure turbulence is, by the way. I found this on the website. I know we had a sensor that did it. I have no idea how anybody used it. How do they locomote? How do they move? So this is how the sea glider worked. We had an external fairing. It was a fiberglass fairing with wings and a tail. We had an aluminum pressure hull that actually did flood around that. The fairing was really just to provide aerodynamic capability. And then we have what we call our variable buoyance engine, which was basically a bladder we pumped oil into and out of the inside of the vehicle. Just changing the volume of it, that basically drives the vehicle to either float or to sink. The body generates lift, and we can shift that large cylinder in the middle around, which was our battery as well. And so we could rotate it, or we could shift it back and forth, and we could literally fly through the water. The equations that govern the flight of the vehicle are aerodynamic equations with simplifications for water. This is an extremely exciting mission. Start at the surface, do a giant V, come back up at the end. We looked at some additional mission types, as well as being able to persist on the bottom to measure radiation, being able to follow things like thermoclines, temperature variations in the water. We did look with our mammal sensor at possibly being able to do some simple form of geolocation and then being able to try to track on that mammal. These vehicles don't move very fast. I mean, we were moving at maybe 30 centimeters a second. You're much slower than most mammals that are out there, so you're probably not going to get them.
So what's the glide ratio and the ratio between the depth that you have to go to and travel at a certain distance?
So we generally didn't get up to speed that we could control the vehicle until about 50 meters down. Depends on how the vehicle was weighted. If you see in this image here, there's these white strips. That's actually styrofoam. So based on the density of the water we would be flying in, we would either add lead or styrofoam to the vehicle to try to position it right at the midpoint of where we would be neutrally buoyant. So we would have to pump and bleed oil in a very limited fashion just to conserve energy. Does that answer your?
Well, a little bit. So I was comparing with airplane because of the aerodynamics.
Oh, the aerodynamics.
So say a commercial jet liner to travel a mile, people need to descend by 15% of that.
Yeah.
So I was just wondering if you go down, say, so 50 meters.
Yeah.
If 50 meters down, how far can you go?
How far can you go?
To reach
You-
the surface?
I think a minimum velocity was something, depending on the vehicle configuration. Let's say you needed 12 centimeters per second. So you just kind of had to calculate the slope of what was the minimum slope you could do to
Yeah.
maintain that. I think the minimum was the actual sort of straight line ground you could cover would be something like 8 miles. It may take 4 hours to actually make that transit. At one point we figured it out. It's been a few years since I worked on this. I don't remember how it worked out. It wasn't very far, but because you can persist in an area so long, you can just keep doing repeated measurements over and over again. You generally didn't cover that much ground though. Another glider. This was sort of the articulating tailfin that I mentioned. It's both a weakness and a strength. It's a sea glider. We couldn't do shallow water operations. We just could not get the velocity up in shallow water to be able to fight currents or anything else. But with something like this, you actually can control your motion fairly well. You can operate in shallow water. And in fact, I think this vehicle is made to work in rivers and along coastlines and things like that. You can take pictures of it too, because our vehicle never gets moving until it's well out of the photo zone. This is another interesting one. I've never actually seen one live, but it has this sort of articulating fins, and it uses the motion of the waves to propel itself through the water, and then it powers itself using solar panels. It's kind of an interesting design, just sort of floats on the surface and drives around. A lot of different techniques for achieving motion. So who flies these things? There's a lot of organizations around the world. There's ANFOG, which is in Australia and monitors a lot of the Pacific Ocean. You have University of East Anglia, who does a lot of measurements. You have SOSIP, who's over in Europe and Spain. You have the SAMS, which is in Scotland. And all these organizations make their data public and available. So you can actually go on, see where they're flying gliders at, what data is being collected if you ever want to apply a deep learning technique to various things. It's kind of interesting. Why do they do this? Climate change, environmental monitoring, oil and gas industry regulation. The oil and gas industry requires there to be current measurements and actual measurements of the current before they start drilling, so they can see what the effect will actually be on their tooling. There's surveillance, ISR. If you're trying to actually see how visible you are under the water, you probably want to know the temperature and how much light's in the water and various things like that. Geological mapping, to actually do surveys of the ground, of the seabed. They will take air cannons and fire them into the ground, and then they'll try to record that signature using a hydrophone, and then they can derive some information. In order to do that, you have to get the hydrophone down under the thermocline, which means you have a very long cable. But you can take something like a sea glider, send it down deep, have it persist, drive around firing your air cannon, have it surface, collect all your data, and you didn't have to go to nearly as much trouble. And it's science. I mean, who doesn't want to? That's all I had.
So how long can these run for underwater?
So Sea Glider was about 9 months. If you if you flew at the shallowest angle that you possibly could, you dropped your sensing rate. You basically did as little work as possible. You could get one out for about 9 months. People generally don't fly them that long. The batteries in them are lithium, and they build up a chlorine gas and basically turn into a small bomb. So if something gets down to low power, you really don't want to pick it up. With the gliders that we put radiation sensors on, we actually had an automatic scuttle. So basically, you got a fiberglass shell, you're flying through radioactive water. How do you clean it? How do you actually get that material out? We just decided to sink them. It was easier and cheaper than cleaning it.
So this is the 9 months is running off a single battery charge? There's no recharge when it comes to the surface?
No, not for Sea Glider. It's just out there.
So how is the data collected? Is it all at the end, or is it transmitted?
So both. It actually connects to the Iridium satellite network. It sends data back, and then it actually picks up new commands, and they come onto the vehicle. It does store all data locally just in case. There's a number of backup mechanisms. There's an acoustic transponder on the front of it. So if you do lose your sea glider, you can hopefully, if you know where it was, go out and start pinging it and find it. We also equipped ours with mammal tracking tags. So if the battery did die and it was on the surface, we could hopefully track it down. They don't. So that's why the acoustic Doppler current profiler I mentioned was so interesting to researchers, because they actually could track position underwater, at least make an estimate of where they were. We have a compass on board, and then it's a pretty decent physics model of the vehicle, so you know based on where the mass is currently shifted and your current depth. So you have a depth sensor, you can pretty much guess where you're at. But I know we ran a test to try to see how accurate we could be on surfacing. You know, go down for the longest possible. This is where I was doing the math to figure out the longest possible dive. And we surfaced within about a kilometer where we thought we were going to be, which in a large space like the ocean, you felt pretty good about it. Yeah.
How big is it?
Sea glider is about, I think, 3 meters, if I remember right. The body of the vehicle, if I was holding along, would probably come up to about here. Then you add the antenna on, and it probably goes up to about here. The antenna's 2-3 feet.
Did a lot of them get hit by boats?
A lot hit by boats, shark attacks. Yeah, shark attacks, and getting stuck on underwater ledges. Like Roomba, it's stuck. We had many. You get a glider. You will lose a glider about every 5th mission. It's just, it happens. Actually, the ones we put the current profilers on, we went down to Antarctica and flew them, and they got trapped between glaciers, and we couldn't actually get them, or icebergs. We couldn't get them out. The ship captain would not go in close enough to actually pick up the vehicle. So we kind of hope the next spring maybe they bring it again. They did.
What's the deepest where you've gone?
So we took ours down to 1,000 meters, or close to it, 900 or so. We were usually pretty conservative. So if you're flying a customer's vehicle, the deeper you fly it, the more energy you're using from their vehicle. You don't want to run your battery out. I mean, it's for them to fly. They are working on a glider that will go down to, I think, 6. It uses a lot of the same internal mechanics. The body is very different. It doesn't have an aluminum pressure hull. It's carbon fiber, so it compresses better. They actually found that the body compressed so much that the oil bladder didn't work anymore. You couldn't build enough volume, so they had to find some special materials that are, strangely enough, used in cosmetics, which actually expand under pressure. Then they had a problem with that because by the time they got to the surface, they would fly out of the water. It's too buoyant. Yeah.
Can you clarify how the oil pumping is affecting the weight of the vehicle?
Not the weight of it, the volume.
Volume?
So we adjust the volume of the vehicle. The weight stays the same.
So what does it mean to affect the volume?
So if
Where are you pumping from to?
so there's inside of that pressure hull, there is a. So in here, this is actually a reservoir. This is the bladder. So we bleed oil inside, and then we push it back out. And this is all within this pressure hull. So we adjust the volume of the vehicle. That changes its volume.
So water takes the place of the oil.
Yeah, I mean, from the outside of the vehicle, the
Yes.
thing crushes basically. So when we would build them, we would actually pull a vacuum on the inside, so that all we would have to do is basically open a valve, and the water would just flow, or the oil would just flow inside. And then we had a pump that would basically pump that oil back outside to increase the volume and increase our buoyancy.
I just said vacuum because that's the only way I figured it could work.
Well, so underwater, it works great. I mean, you're 1,000 meters down, the pressure is enormous. On the surface, though, it doesn't work so great, so that's why we pull the vacuum.
So this is kind of like a general vehicle, like, and for different projects, you're going to load different sensors or something
Yep.
for the customer?
Yeah, so there was only so many sensors you can put on them just because of the weight of the vehicle and how much volume it could actually displace. We would put Kind of depended on the sensors and their power draw as well and the length of the mission. Like when we flew the radiation sensor, we only flew the radiation sensor. When we flew the acoustic current profiler, only that. Frequently we fly our conductivity sensors and what we call our PAR sensors, our light sensors. Those were common packages that went together. As long as we developed a new version of this outside fairing that had a larger capacity space in the back so we could put more, and then we had to start adding foam because we just didn't have the buoyancy to actually float the vehicle.
How much of the software changes from mission to mission?
None really at all.
I know.
So we use a generic data format that essentially reads a piece of sensor data, applies a generic header to it, and then just dumps it to a file on the disk. The only sensor on board that we really relied on for flight was the salinity sensor and the depth sensor. So those two we would look at to try to figure out what we needed our flight path to actually look at. What's the buoyancy of the vehicle, and then how fast are we going as we're underwater?
But I mean, to program the path, is that a code? Is that a
It's all
file?
code. It has a pretty basic algorithm inside. Essentially, you start on the surface upright, you aim yourself, and then you just start to sink, and then you just try to maintain that heading. And then you basically just do this large V shape over and over again. If you want to fly to different waypoints, those are programmed into a file, and you just kind of remember exactly which one you did last, and you dive until you get the next one.
Can you communicate with it while it's
No, we can't. When it surfaces, it calls back in over to the Iridium satellite number, and then you can transfer commands with it. We didn't have any live sessions with them for the most part. We could park the vehicle on the surface and get sort of a pseudo live session. It would basically just keep dialing in over and over again.
If you had a boat nearby, there's no way to communicate with it.
No, we didn't put anything on it like that. We did look at acoustic modems, basically taking moored sensors, putting them on the bottom of the ocean, and then trying to dive down and do some data transfer. This thing isn't really that accurate, and the acoustic modems are really slow. So it was a research project. We didn't go too far with it. Oh.
So was there any onboard diagnostics that could monitor its own status? And if so, could it in any way try to react to any form that what's up? Like if it knew its battery was getting down, would it be possible for it to try to head somewhere that it could be more easily picked up?
Yeah, there was actually an emergency pickup point that was programmed into them. It could be triggered by a variety of things. We monitored the rate the motors were moving at. If we thought they were going too slow, it would trip a warning, and it could basically surface and then call back in, and it wouldn't proceed until it got some information. We didn't like, it was great to have, but it was also dangerous. This thing on the surface, that mast, you just get blown all over the place. I've tried to pick them up. It'll surface, give you a GPS coordinate, somebody will call you on the satellite phone, you get over there, and it's moved 300 yards away because of the wind. The surface is not something you want to spend a lot of time on. It's dangerous. There's a lot of stuff there that could hurt you. Boats, sharks. We did have some interesting things with it that we could tell from the telemetry, but they had to be fixed by a human. One of those, we frequently see the vehicle listing to one side. Because it's out in the middle of nowhere, we really don't know why, but it would look like something had attached itself to the vehicle. And so usually what we would do is we would go deep and see if it fell off. And usually it would. We come back up and we're flying fine, so we're like, all right. A lot of this you're flying blind. You get telemetry back, and you can look at it and try to guess what the vehicle's doing, but you don't actually really ever see it move.
How much processing power do you have on that model, and are you using embedded processors so you go to sleep?
So this has the same processor that a TI-85 does in it. It's pretty awesome, yeah. It actually runs Pico DOS. A lot of the oceanography community likes these particular processors for some reason. This was developed at the University of Washington in their Advanced Propulsion Lab. So they chose one of these. It was fantastic. Yeah.
When it surfaced, when it came up on the surface, was it possible to maybe gather data from accelerometers and stuff and try to guess which way it's going to take?
We use GPS actually a lot for that. We actually had a Kalman filter on board to try to correct for various errors. It was a really bad implementation of one, and it took about 5 minutes to run. So we didn't use it very often. Yeah, it was really I didn't write it. Anything else?
So as I was understanding, you got a mechanism to steer.
Yep.
So how's that mechanism?
So in the middle, that large cylinder that's right there in the middle is the battery, and so it can actually rotate itself. It's actually not a complete cylinder; it's just like a half. So it's basically half a cylinder. It can rotate itself and it can shift back and forth. So it leans. Yeah, it does. It literally leans. It's like, no, go this way, that way. Yeah. Which was interesting because it actually, I can't remember, on the way down, if you lean to the right, you would go right, but if you were on the way up and you lean to the right, you actually would go left. You kind of got to picture in your head a plane flying. It sort of makes sense.
How does it propel itself?
Just by the motion of sinking or rising. So only by adjusting its volume. When it gets up enough velocity one direction or the other, the body just generates lift, and then you can actually, those control surfaces start to take effect. We played around a lot with different sizes of wings, different sizes of tails, trying to figure out if we could get better control in higher current environments. Sometimes we would adjust them. I'd see the mechanical engineers coming up with like, here's a really long tail, and I don't know if they ever really made that much of a difference. Minimal power consumption. So you actually try to, so before we go out with one of these, we'll look at the approximate density of the water in the area we're going to be flying, and we will try to get a gauge of what the actual volume of the vehicle is, and then we'll measure the mass exactly. I mean, we would go through every part of the vehicle and actually measure it. And then we will try to adjust the lead or foam on it so that we're essentially neutrally buoyant when we're at some particular volume, so that we can do as little work as possible in flight.
How many up and down trips are part of a normal mission?
So I saw missions that were as short as 2 weeks. They were sampling pretty heavily and driving against some hard currents. They were doing a lot of pumping of oil. And then we had missions that went as long as 9 months. It depends how hard you want to drive it. If you're going really fast, you're probably going down really fast, and you're going to have to come back up sooner. You're probably going to get much more of a sawtooth.
But what's the duty cycle on that? Like, you're coming up once an hour?
Depends on what you've configured it for. What depth do you want to go to? What glide rate do you want?
So like what's a slow rate, what's a fast rate?
So I think it's like around 12 centimeters per second you needed at least to get lift on the vehicle. If you were up around 30, you were basically just plummeting into the ocean. You weren't really actually controlling it in any way. I did use the 30 one time to fight against a current and basically nosedived into the ground during the tide, as the tide was going in or out, to try to anchor myself. It really just depends on the researcher. Depending on the sensor suite you actually have as well. So one of our connectivity sensor required a very slow, uniform flow over its surface. So people would try to basically put it on a particular tangent and just kind of let it glide down, so they get good measurements.
I think you mentioned speed, flying. What's the typical speed?
So typical, like I said, you can go anywhere from like, let's say 12 to 30. I'd seen things like centimeters per second. Yeah, it wasn't very fast.
Oh, that's pretty slow.
It's pretty slow.
Because for average swimming,
in the water.
1 meter per second. 1 meter per second.
It usually is enough, though, to station keep. So if you want to stay in a region, it's better than a float.
And if you come across riptide, we just get blown out.
Near coast, it was not good. We put one of these in off the coast of North Carolina to see if we could operate in 20 meters of water. And essentially, I think we picked it up in Virginia before. I think there's a current that sweeps up into New England. And we went out and got it because we're like, we're going to pick this up in Massachusetts. We're going to have the Massachusetts guys get it from there.
Way home.
Sorry, does somebody else have a
I
question?
mean, the glide find the way home. Started from Massachusetts.
They do have a sticker on the side of them. We picked up several. We had one that disappeared in South America. It suddenly appeared a couple days later in the back of some guy's truck. They had to send a guy down from the embassy to go pick it up. We had another one get lost in the Philippines. The guy that picked it up there, he was a government official. He would not believe us it didn't fly in the air. He thought it was an advanced flight. Yeah, it was like, no, it's not. From the Yeah. It's a fun project. It's pretty interesting. We'll bring them on the site.